All right, guys, for 4.5, concavity and points of inflection, and we're going to talk about the second derivative test that explains relative extrema. Okay, remember relative extrema is relative maximum. So, first of all, what is concavity? Well, it's concave up or concave down. A graph with this shape right here is called concave upward or concave up. The tangent lines below the graph, so you see all the tangent lines have to be below the graph, and the slopes of the tangent lines are increasing. What that means is that as you go right, your slopes are increasing. So let's say this is a -1, 0, 1. So as we move to the right, it's increasing. So that means the second derivative is greater than or equal to 0. Okay. Now, a graph with this shape is called concave down. So the tangent lines lie above the graph, and the slopes of the tangent lines are decreasing. So see if this were 1, 0, and then -1. So that's what that means. So the second derivative is less than or equal to 0. One of the ways to help us remember these things is concave up looks like a smile, concave down looks like a frown. And I want to show you with colors here. We have a concave down right here because it frowns. And on the other side, we have a concave up because it's kind of that half smile right there. Now this point, which the concavity switches, is what we call the point of inflection. So it changes the concavity at that point, okay? And that there is a tangent line. So change of concavity is points of inflection. Now, some textbooks use other definitions for the point of inflection. They don't require that tangent line. Usually I just think of it as the change of concavity, but it's not a big issue to prove or not on the AP test. We will go through how to define things specifically and write them down to get points on the AP test, okay? So examples. So use the graph as the right to answer these questions based on your answers on the appearances of the graph. Okay, on which intervals is the graph concave up? So think of where it's making that smile. Okay, so if I were to make that smile, I see I'm making an upward smile right here. Here I'm starting to frown. Here I smile. Here I'm frowning. Here I smile. And I'm frowning. And I'm not making anything right there. So now that I see that, now I can write down my concavity intervals. And remember, the intervals are with the x value. So we start at -2, and we're going to -1. We start at 1, and we go to 3. And then we start at 4, and we go to 5. All right, now what intervals is the graph concave down before I use the orange? So I'm going to use the orange now. Concave down, so that frown, well, we're frowning right here. If you look we're not frowning here, right? This is a line. So it's not, concavity is about that nice curve to it. This is the line, so we don't have any concavity here, but we do have a frown right here. So that means our downward concavity is from -1 to 1 and 5 to 6. Next question. On which intervals does the graph have no concavity? Well, again, no concavity, we have it from 3 to 4. And even though it's hard to see right here, our endpoint is actually at 7. And this is a line too, it's a horizontal line. So it's 6 to 7. What are the points of inflection? One thing I want you guys to notice right here is this point of inflection. So it's an x comma y value. And remember that the points of inflection is where it changes concavity. So where it changes concavity and where it would have a tangent line at that point. I know before we were saying, well, some people consider it and some people don't, but even though you think we have a change of concavity right here, we actually have more than one tangent line here. Can you see that? Because it is a sharp turn. So this would not be considered our point of inflection. We have a point of inflection at 1, and the y value at 1 is 1. And we have another point of inflection right here at 5, and that y value is also 1. So again, no point of inflection here because it's a sharp turn. Okay. Analytically, we find concavity intervals and points of inflection by using the second derivative number line. So second derivative, do our sine ray, so on and so forth. The procedure is parallel to the procedure used in the last lesson to find increasing, decreasing. Okay. Most textbooks use open intervals for concavity. So remember, for increasing, decreasing, we were using closed, and for concavity, we use open. However, there is no universal definition for concavity, so there is some chance for ambiguity. So if you're using, you'll see that most textbooks might use parentheses, the open, but in some they might use the bracket, the closed. So it goes back and forth, and you will not be deducted with that on the AP test like we talked about with the increasing, decreasing. All right, so let's do some of the algebraic stuff, okay, without the graph. Determine the points of inflection and discuss the concavity of the graph. All right, so we see that here we have no domain restrictions because that's always step 1, just like in increasing, decreasing. So we take the first derivative because we have to put the first derivative to find the second. So we get 4x cubed plus 3x squared minus 6x. Okay, we're not worried about increasing and decreasing right now. We're going from concavity, so I'm going to go straight to the second derivative. And we get 12x squared plus 6x minus 6. All right, just like in the previous section, we need to find the critical numbers. The way to do that is to set that derivative, the second derivative in this case, to 0 and undefined. Well, right away we can see right now that the second derivative will not be undefined anywhere. This is a function continuously. So we're going to set it equal to 0. The first thing I notice is I can take out a greatest common factor, leaving 2x squared plus x minus 1. Then you see I can factor this out, so I get 6 times 2x minus 1 times x plus 1. Okay, I know it might take you a little bit more time to factor that, but it's okay. Now, we know that f double prime is never undefined. We just went over that. But we know that f double prime is 0. So f double prime equals 0 when x is 1/2 and x is -1. So we get that from these values right up here. Okay. Now we need to do our sine ray. So let me put that in order of -1, 1/2. All right, let's do our sine ray. We end up with minus plus plus, minus minus plus. So two negatives make a positive. Negative positive is a negative. Positive, positive, positive. Okay. So what I like to do, just like I did in the increasing, decreasing, is kind of show the diagram for it. So concave up, concave down, concave up. All right, now we are here to do the points of inflection. That was the whole idea of this, and concavity. So the points of inflection are where they change concavity. So we see points of inflection are at x equals -1, but we have to plug in to find the y value. You plug into the original problem. When we plug into the original problem, we get -2. The other point of inflection, because we change concavity at 1/2, plug in 1/2 to the original problem, we get 7/16. All right, that was step 1. Now we need to discuss concavity for the graph. So concave up, concave down. Okay, concave up, we will go from -infinity to -1 and 1/2 to infinity. Means our concave down is -1 to 1/2. We're done there. All right, that was probably the most simplest of functions. Now let's see if we can go into a more difficult one. If f of x equals x squared plus 1 over x squared minus 4, and f prime of 2. Hey, they gave us the second derivative already, so we don't need to find it. So watch out for that. Usually they'll do that if it's a more complicated second derivative, so that way we don't have to worry about simplifying it. So we're going to list the intervals where f is concave up, concave down, and list the points of inflection. So this is the second derivative. We have to find where f prime is undefined, where f prime is 0, and we also have to keep in mind our domain restrictions. So domain restrictions come from our original problem. So here's our original functions. What can't x be? Well, as you can see, x cannot be -2 or 2, right? Because that would put 0 in the denominator, and we can't have 0 in the denominator. All right, now we're going to look at the second derivative and see where we have undefined and 0. All right, so let's do undefined. Undefined comes from the denominator again. It can't be 0, so the two values are x equals -2 and 2. Where is it 0? Well, let's talk about the numerator when it comes to 0. This will never be 0, because no matter what number we put in for x, we square it, becomes positive. Then we add another positive onto there. It's always positive. It will never be 0. All right, as you can see, our critical values here are the same as our domain restrictions. So when we put it on our number line, I want you guys to keep in mind that these two critical values are actually the vertical asymptotes. So I'm going to draw that in so we remember that. Now, when we do this, let's see, we have to remember we have negative, positive, positive, negative, negative, positive. It's cubed here. So actually, we don't have to worry about that. And we're squared, so we're all set right here. Negative times a negative is a positive. Negative times a positive is a negative. Positive, positive is a positive. Let me do my drawings because I get used to that. Positive means concave up. Negative concave down. Positive concave up. All right, let's do concave up, concave down before we do points of inflection, because that we have to discuss something. So concave up would be -infinity to -2 and 2 to infinity. Concave down is -2 to 2. Okay, what about the points of inflection? Well, points of inflection would be where it changes from concave up to concave down. And usually we would say right here and right here, right, at 2 and -2. But you can't have a coordinate at an asymptote, right? It never gets there. So how can we have that point? So actually, since where our points of inflection would be, and they don't exist, we do not have one. So none. So watch out for that. All right, one more thing, guys. The second derivative test for relative extrema. Remember, relative extrema is your relative max and min. So how can we use our second derivative to help us find max and min, especially when the second derivative is supposed to tell us where our concave up, concave down is. Okay? So this test does not require a second derivative number line. It does not find points of inflection. It is used to find relative extrema. That's what I just said, max and min. So here's what we're going to do. We're going to use f prime to find the critical numbers. We're going to plug the critical numbers into f double prime and analyze the concavity to determine if the function has a relative max or min. The second derivative test does not always give the answer, but it tells us if it's a max or min, okay? So, example, use the second derivative test. So we have to do it. We have to use the second derivative test to find the relative min and relative max of points of the given graph f of x equals -3x to the fourth plus 6x squared. Okay, so remember, we're using f prime of x to find the critical values. So f prime of x equals -12x cubed plus 12x. So what I'm going to do is simplify that out so I can find that those critical numbers. So if I take out a -12x, I'm left with x squared minus 1. Don't stop there because that's the difference of squares. So we get -12x times x plus 1 times x minus 1. So when is f prime 0? So we have our critical numbers at x equals 0 and x equals -1 and 1. Don't forget that the reason why we're finding these are critical numbers is because we're setting our derivative equal to 0. All right, so these are our critical numbers. Now we're going to plug them into f double prime. So let's find f double prime. We get -36 plus x plus 12, x squared, sorry, plus 12. All right, so I'm not worrying about simplifying right now because I'm just plugging in. The next idea is to plug in our critical values. We're going to plug in -1 to the double prime. We're going to plug in 0. We're going to plug in 1. When we plug in -1, we get -24. When we plug in 0, we get 12. When we plug in 1, we get -24. Okay, so what does that mean? Well, if you look where it's negative in the second derivative, that means it's somewhere on a concave down, because negative means concave down. Where positive means concave up on that second derivative. Same thing down here, negative concave down. The reason why I drew these out is because what do you know? What does that mean? What does that mean this is? Well, look at guys, it goes increasing to decreasing, meaning it's a relative max at x equals -1. Do we know what the whole coordinate is? No, but we do know it's a relative max. Where 0, as you can see, it goes decreasing to increasing because it's on a concave up. That means it's a relative min at x equals 0. And for 1, since it's on a concave down, it's a relative max. Now, for us, we have the original problem, so we can find the points by plugging into the original. If we didn't have the original, let's just say we had the derivative and the second derivative, then we wouldn't be able to find the y values. But because we are able to have them, and it's asking for the points, it means we plug these guys back in. So our mins, our relative mins, are at, well, if I plug in 0, I get 0, 0. And our maxes, we have 2 of them. When I plug in 1, I get 3. And what do you know, when I plug in -1, I also get 3. All right, one more problem, guys. Okay, g of x is a function with some derivative value shown in the table. So this is one where we don't have the function. All we have are these coordinates. Find the x values of the relative max and the relative min points when possible. Okay, so remember the first thing we did was we found the critical numbers. And the critical numbers are when our first derivative equals 0 or undefined. So on g of prime, where are our critical numbers? Well, that means our critical numbers are x equals -3, -1, 0, and 2. Again, that's because our first derivative is 0 at these points. Now what we need to do is take our second derivative and plug in these critical values. So what I'm going to do on the side is say g double prime of -3, because that's a critical number. G double prime of -1. G double prime of 0. And a lost space, g double prime of 2. So let's use our table now to fill this in. At -3, we have the value of 4. At -1, we have the value of -1. At 0, we have 0. And at 2, we have 3. So remember, for this, we are looking at positive negatives. So at -3, it's a positive 4. So it is concave up. At -1, it's a negative. So it's concave down. 0 is neither positive nor negative. So we don't have concavity. At 2, it's a positive 3. So that's concave up. All right, so we have a relative min, and if you see, we have a min at 3, -3, and at 2. And it just says I want the x values, so I just have to state that at -3 and at 2. Now, how do we know that if we were to explain why? Well, that's because g prime of our x value equals 0, and g double prime of our x value is greater than 0. We have a relative max at x equals -1 because g prime of x equals 0 and g double prime of x is less than 0. Okay, so sometimes we're able to use it and sometimes we're not, depending on what's given to us. We didn't have the original function, that's okay. We didn't need the original because we have coordinates that allow us to define what we need to know. All right, let's practice that stuff.